Good morning to everybody. Thank you for being here so early. So I'll be talking about this, but I guess I have to start by explaining what these unitary invariants are. And I bet you will have seen it before, okay? So these unitary invariant properties that I'm interested about are properties of a set of states that doesn't change if you rotate all the states by the same unitary. So in a sense, it's the properties that are basis independent. So if you talk about set of states, you want to say things that are gauge invariants, that are physical, and that don't depend on the basis you're picking, okay? So, and these states, they can be representing both preparations that you do and measurements that you're doing, okay? So it's natural that if you're looking at only these unitary invariants, you're looking at the physical content of a certain protocol or a certain, something that you're doing, or some property of measurements and protocols that you're doing. So these invariants, they are geometrical. And it's a mathematical fact that they can be all described by this kind of invariant, which has a very simple form. For pure states, it's just, they're called Bargmann invariants, kth order, if you have k of them, k states here. And they are just the inner product of state A with B times inner product of B with C times C with D, and then the last one with the first one here. It's a cyclic thing, okay? If they were mixed states, they are trace of row A, row B, row C, row D, row E, and so on, okay? So these are the invariants I'm interested about. And I'm interested in them because using only those invariants, you can describe any unitary invariant property of a set of states. So they're very simple in form, and you can use them, okay, to give a complete description of the properties I'm interested in. So the simplest invariant appears when you have only two states. So you have the inner product A with B and then B with A. And that's just the overlap, okay? And when I say overlap here, it's modulus squared of the inner product, okay? So this is the simplest one. It's a probability, we all know. But if you have three states or more, for three states, you already have this form, and this is a complex valued quantity, okay? Where do these things appear, okay? Where do third order or fourth order, fifth order invariants appear in quantum mechanics, okay? So we'll see a few places where they play a role. So as I said, if you have a preparation and a measurement, the overlap gives you the probability. So we're very familiar with these probabilities, right? So it looks like in order to get invariants like this, you will need something like a sequence of measurements or a sequence of states, you know, transitioning between one and the other or something like that, okay? So that's an intuition about where these invariants will appear. And this is a place where these invariants appear. It's a very simple setup. It's a geometric phase experiment, okay? So you have a Mach-Zehnder interferometer. So this photon with polarization A goes in a superposition of the two arms of the interferometer. And only this arm, you put some polarizers that project onto polarization states B, C, and A. And the other arm, you don't do anything. This compensating device is just because some photons will be absorbed here. So you want to absorb photons here so that you can better see the interference fringe that appears, okay? So you see, only this arm, you have a sequence of projectors. And of course, you're not gonna use orthogonal projectors, otherwise no photons will go through. There are non-orthogonal projectors, okay, polarizers. And then what you see, okay, some photons are gonna be absorbed here, that's one thing. And you also see that the fringes here, they depend on this sequence of polarizers. So depending on the sequence of polarizers, you see a different interference fringe, okay? And you want to understand this fringe. And this fringe, I mean, this sequence of polarizers is taking the state of this arm in a cyclic path in state space, okay? And when you look at the phase that appears here, that controls the interference here, it is exactly the phase of these states, where these states are the initial polarization and the eigenstates of this polarizer, and this one, which has to be the same as this one for the cyclic thing to happen. Okay? So if you're interested in the fringes here, you're interested in measuring exactly this phase that appears here, which is the phase of this complex quantity. And of course, if you put 4 polarizers, 5 polarizers, you're going to be measuring a fourth order, fifth order invariant. Okay? So this is a very simple place where invariants are affecting the outcome of physical experiments, okay, in a geometric phase experiment. And one thing we did related to this, okay, is to understand the possible values that this quantity can take, okay? And actually for 3 states, the picture is really pretty, okay? For any number of states it's pretty. It's this droplet figure. So this is the complex plane, and you're looking at the complex values that this quantity can take if you take quantum states. And we can prove that they have to be inside this droplet, not outside. But this droplet goes from 1 here. This is 0. It can be a bit negative, okay? But it's an amplitude. In principle, you might think it could be anywhere in the unit disk. But actually, it's a very restrained, very constrained shape inside the unit disk. These are the possible values if you take states of any dimensionality, but they're quantum mechanical states, okay? So in order to get some value outside here, it would have to be a beyond quantum mechanics, okay? Super quantum states. But quantum mechanics, you have to be inside here. So what does this tell you about the experiment there, okay? This is the modulus of the number, of the complex number. And this is the angle, the phase that appears, okay? So if you understand this trade-off, you understand, for example, that if many photons go through, you have a modulus which is close to 1, then the phase that you can observe is constrained to a very small value, around 0, you see? So there's a trade-off. It's a quantitative prediction about what fringe can you see if you're observing a certain absorption of photons in this experiment. So understanding this shape tells you about these experiments, okay? So we managed to prove the shape of this thing in these papers for 3 states and any number of states. See also this paper by Xu, who independently obtained the characterization for any number of states, okay? So this is one place where these invariants appear. But over the last few years, I've been pushing a program, a research program, to look at the role of these unitary invariants and to explain many foundational phenomena in terms of these invariants, okay? So these are some of the papers that we put out in the last few years. Many years ago, we together with Daniel Broad, we started looking at basis-dependent witnesses of coherence, okay? That you can propose for these. Now you're talking about a few states. Just by comparing them and using these quantities, you can tell if these states can be simultaneously diagonalizable or not, without making reference to any basis, okay? You can have a witness that these guys cannot be diagonalized just by measuring these unitary invariants, because certainly this is not something that depends on the basis. You're talking about any basis, okay? Can be diagonalized in any basis or not. Kirk-Dirac quasi-probabilities, they are quasi-probabilities that can be not only negative like the Wigner function, but they can be complex, okay? And they are third-order invariants. So when you characterize the shape, you're saying, look, the KD distribution value in each phase space point has to be inside here. So you're saying the minimum value, the most negative. You're saying what the complex value is, the imaginary part. And these things have been related with advantage in metrology, okay? We looked at weak values and how to describe them as invariants. Ways to certify non-stabilizedness using overlaps. We obtained all the contextuality inequalities of the exclusivity graph approach. They can be obtained as classicality inequalities for overlaps, looking at the overlaps of states. And here, so this is nice because it makes a connection between these coherence witnesses, which are independent of basis, and non-contextuality inequalities. They're actually the same thing, okay? It's just that you can look at one state as being preparation and the others as being measurements. And you're finding bounds for non-contextual models the same way you're finding bounds for coherence-free states, states that can be diagonalized, okay? It's the same thing. And finally, these are useful for the characterization of multiphoton distinguishability. And that's what I wanted to tell you more about now, the rest of my talk. Okay? So this is if you're interested in any of these topics, please come and talk to me, okay? So where do they show up in photonics? This is the Hongo-Mando experiment. It's just a 50-50 beam splitter with 2 photons going into different modes of the beam splitter. But these photons, they have different wave functions describing their internal degrees of freedom. Think of that as polarization, okay, for example. And the interferometer doesn't mess with polarization, okay, just path. But if you put them and they're perfectly indistinguishable, they always come out together, either here or here. That's the Hong-Mandel effect. But if you're partially distinguishable, like these colors here, then the probability that they come out separately gives you an estimate of the overlap between the wave functions of the two photons that went in, the spectral functions, like the polarization, okay? So this is a way of measuring the overlap between these functions by doing a very simple interferometric experiment. If you have 3 photons or more, like you do in photonic quantum computing, you have many single photons, and you do interference, very complicated interference, like boson sampling experiments, okay? Then the outputs here, they can depend not just on the overlaps, but also on the phase of these higher order invariants. For the case of 3 photon experiments, there's a single phase that matters, okay? And this appears explicitly here, because this is a probability that they come out separately in the Fourier interferometer, okay? It's an explicit function. And you see that the phase here affects the outcomes. Actually, we know now that the only quantities of the single internal degrees of freedom of the photons that matter, that affect probabilities at the outcome of linear optical experiments, are unitary invariants. So if you want to have a complete description of what these photons are how these photons are going to behave in an interferometric experiment, it's sufficient to know the invariants, and actually a complete set of invariants. That's something that we know how many you need and so on, okay? So that's a very important way of characterizing multiphoton distinguishability. These effects, they're collective effects. They only appear in 3 photon experiments, say, right? 2 photon experiments, these things don't show up. And they are known in photonics as collective photonic phases, but the collective photonic phases are phases of invariants, okay? So I'll talk about the phase of these complex numbers that I was telling you about, okay? And on Thursday, there's a talk by Michał Osmaniak, okay, on a way of certifying multiphoton distinguishability using this knowledge of invariants, okay? Now I wanted to talk about some features or some things that we managed to work out for linear optical experiments because of this understanding that we have about how they depend on unitary invariants, okay? So for simplicity, let's look at a simple 3 photon experiment, like here. And we're gonna send 3 photons into a QFT interferometer. When I say a QFT interferometer, it's just a linear optical device with many beam splits and phase shifters, such that the unitary that describes creation of the mapping of creation operators before the interferometer and after, it's a QFT transform, a Fourier transform, okay, of 3 modes. And now you can look at the output here, and we all know that photons bunch, right, and fermions don't, right? And then we know what a Bose-Einstein condensate is, right? And we know that bunching is a characteristic of photons, right? So here we're looking at 2 different ways of measuring bunching. 2 figures of merit that are affected by the way that photons bunch at the output of this QFT, okay, or any other interferometer. The first is the probability of bunching, is the probability of some collision, meaning at least one mode has at least 2 photons, okay? So for example, 210 as occupation at the output is a bunching event. 300 is also a bunching event, okay? But it's enough to have 2 photons in somewhere, okay? The other figure of merit for bunching is the probability of full bunching. So the probability of full bunching is the probability that all 3 photons are gonna come out in the same mode, I. Okay, so that's a different thing, right? Because it doesn't include these events 210, for example. It's only 300, 030, and 003. Okay, it's the sum of these 3 for this simple experiment, right? So what's counterintuitive for these 3 things, okay? One thing that's counterintuitive for the probability of bunching, for the QFT, you have this expression, okay? And the first thing is that the probability of bunching is minimized by indistinguishable photons, okay? So if you had the intuition that indistinguishable photons bunch a lot, actually this is the opposite, okay? The scenario where the photons are gonna bunch less, the least, is the case of indistinguishable photons. And actually, the situation where the photons bunch have the highest probability of bunching is a situation where the photons are very distinguishable, okay? Where the overlap between the 3 pairs is a quarter, and the phase, that collective photonic phase, is the most different from 0. It's pi, okay? So that configuration is very distinguishable, but it is the configuration that has the highest probability of bunching for this QFT interferometer, okay? So this is a counterintuitive effect. And of course, what's playing a role here is this non-classical phase that's making this happen, okay? Together with the symmetries of the QFT, which is the interferometer that we're using, okay? We looked at other alternative interferometers, but this is the one where this effect is the strongest, okay? So this is the counterintuitive behavior we found for the probability of bunching. For the probability of full bunching, and you can see the expression here, you see that the probability of full bunching, all photons are going to come out in a certain mode, I. It increases when you increase the average overlap, but you see there's also dependency on the phase here, right? So this means that you can increase the average overlap and play with this phase here to actually decrease the probability of full bunching, okay? Because of this dependence of the phase, right? And for this to happen, you need to have this phi different from 0. Otherwise, if phi is 0, that never happens. It is monotonous dependency, okay? Increase the average overlap, increase the full bunching. So you do need this non-classical phi, okay? That is an invariant that's not real and positive for this to happen, okay? There are many, many places where this condition appears, okay? The invariants, they are only classical if they are between 0 and 1 and they are a probability, okay? So you see this appear also in this kind of phenomenon. Okay, so these are two different counterintuitive things. And we made an experiment together with, well, I made the theory for an experiment that Fabio Sciarrino performed with his group at Sapienza University in Rome. So quickly, like the experiments uses single photons generated by a quantum dot, and then different pulses generate different photons. You delay a few photons so that all the photons come to the chip at the same time. So they were created by the same quantum dot. They enter the interferometer at the same time. It's a 3-mode interferometer. You send a photon here, one here, one here. And then you use this programmable chip to implement the QFT and also to implement this other interferometer that you append to it, so that you can actually do pseudo photon number counting by splitting the modes into many modes, putting detectors, superconducting detectors, and then you can estimate the probabilities for all possible events up to 3 photons in each mode. That means you can really calculate the probability of all outcomes if you do a 3-photon experiment here. And that's what we did, okay? And then when we did that, you also you can tune the indistinguishability of the photons here by delaying them by different amounts of time so that they have only partial overlap in the temporal function, part of the spectral function that distinguishes them, only partially. And you can also tune the polarization of each photon so that you can play and generate a general indistinguishability scenario for these photons, okay, by playing with these 2 degrees of freedom, internal degrees of freedom. And then what you see here, this is the average overlap, the 3 overlaps of the 3 photons, okay, the average. And this is the probability of bunching. And when you have this phase being classical, 0, as you increase the average overlap, you increase the probability of bunching. But if you have these states with a non-classical collective photonic phase of the invariant, then you can have the opposite effect, which is counterintuitive. You're increasing the pairwise indistinguishability while decreasing the probability of bunching, okay? And on the right here, you're plotting the probability of full bunching, all photons coming out in some mode, versus the average overlap. And in this region, you have the expected behavior. The overlap increases, leads to increased probability of full bunching. But in this part of the graph, now you're talking about preparations which have complex valued invariants, phase different from 0, then you can have the opposite effect. You're increasing the average probability, the average overlap, while decreasing the probability of bunch. Of course, because of this dependence on the phase, okay? And then we did some other things using that, showing, for example, that some useful photonic protocols to distill indistinguishability, like measure some photons, so that the photons that you didn't measure have increased in distinguishability. That's something useful for photonic quantum computation. And we show that knowing this phase is necessary to be able to implement the optimal protocol. So the phase affects experiments and affects experiments which are useful in photonics, that are used to distinguish indistinguishability of photons, improve distinguishability of photons, okay? So that's something else I didn't put there, but it's something else we did. Yes? Deixa eu fazer aqui de novo. Let me do this again, because the computer forgot it's talking to the screen. Now it is. So this is the second thing I wanted to tell you about, photonic indistinguishability, okay? So now we're trying to characterize photonic indistinguishability of the input state by looking at this quantity, which is just the variance in photon number at the output. So we're calculating not the average photon number, but the variance of the photons here, here, and here, and take an average, okay? So the sigma is the variance, the average variance. And we managed to prove this formula, which tells you that the variance that you observe is a function of the interferometer unitary, that's the settings of the beam splits and phase shifters you have, and of the overlaps between the wave functions that describe these photons, okay? So that's a very general thing, and it means, knowing this, means you can do whatever you're doing with your photonic computer, okay? Maybe you're doing a variation algorithm, you're changing the interferometer, tuning it to different values, and you can use the outcomes that you're getting just by estimating the variance, okay, of the outcomes, to keep track of what the photon sources are, what the overlaps are, okay? Because if you do, like, for 3 photons, you can do 3 different interferometers, invert these equations, and find the overlaps, see? So you can monitor the overlaps while you're doing something else. You don't have to stop and say, okay, let's do Hongomandas again to see if the source is okay. You're actually tracking what the source is doing while you're doing general interferometers, okay? So that's an interesting thing to do and to know. The other thing that you can do is to do a semi-device independent certification of indistinguishability. Okay, what do I mean by that? Okay, from that previous equation, you can prove this other one, which is a lower bound for the average overlap. Okay, so now you're using some interferometer, you put the 3 photons there, or any number, n, okay, and you want to know what's lower bound for the average overlap, so that you can, for example, be sure that the photons you're using are highly indistinguishable, right? And this lower bound here, it only depends on the variance that you observe, this average variance of photon number at the output, and on the sigma d, which is the variance for classical light, variance for distinguishable photons, okay? So you tune some interferometer, you measure the variance, you change the lights to be classical, which is a simple experiment to do, and you measure the sigma d, sigma for distinguishable photons. Then this gives you a lower bound for the average overlap, okay? So this lower bound, so if you try, the best interferometer you can do is the QFT, okay? But if you don't do exactly the QFT, you're kind of close to it, but you don't know exactly what interferometer you have, this quantity will still give you a certification of the minimum average overlap you have, you see? So in that sense, it's semi-device independent, because you don't have to trust that you tuned exactly the right interferometer. It's robust. It's very robust, okay? If it's close to the QFT, this thing will be a very good bound, okay? So this is something that's interesting for certification of photonic quantum computation. And there were some experiments done here. in a similar setup to what I showed you using programmable interferometry. Okay? So this is what I had to tell you today. Okay? We went over a little bit what unitary invariants are, how they're related to geometric phases, and how they play a role in multiphoton distinguishability. Okay? So we talked about some applications for these things. And on Thursday, Michał Osmaniak is going to talk about certification of multiphoton distinguishability using these ideas. Thank you. I was wondering, like, can you use this formalism to certify? That's a good question. Well, if we can use the formulas to certify non-Gaussianity of continuous variable states. So in this recent work that Michał is going to be talking about, we show that we can measure these quantities for continuous variable states as well. Okay, so we can certify dimension, we can certify coherence using the same kind of approach because we know how to measure those. But I haven't looked at criteria for Gaussianity from that point of view. So that I'm not sure, okay? Maybe this stellar rank representation of continuous variable states may be helpful for that, okay? Because we may be able to measure maybe the right quantities that you need, okay? But I'm not sure.
More questions? So maybe I can ask, because when you showed in the beginning of your talk, you showed that you go like A, B, C, and K, right? And this is kind of one-dimensional OOP, you can say. Can you also generalize this concept to some two-dimensional, let's say similar, let's say what in condensed matter you have Chern numbers when you have surface integrals, not line integrals? That's nice.
So actually, you can define many things that appear in condensed matter theory. They are still of this form. So you do have these topological invariants. Mm-hmm. You have chirality, which are quantities of that form. So we have also one paper looking at how to measure chirality of spin states, which has to do with whether the spins are on the same plane or not, right? Mm-hmm. So it's kind of a spin texture of different spin models. And you can measure chirality by the same circuits that measure these things for separable states, mm-hmm. except chirality is actually a property of entangled states as well. But the circuits that you use to measure chirality are the same that you use to measure these invariants for separable states. Mm-hmm. So there's a connection there. I don't know so much about Wilson loops and other quantities which have this shape.
Yeah, they look exactly the same as Wilson loops.
Yes, so they have that shape. I don't know if knowing this is helpful. Mm-hmm. Okay, it means that you can measure those spins with a quantum circuit that manipulates them and get an estimate of these quantities. Mm-hmm. If that's known or that's helpful and useful, I'm not sure. In photonics, at least, it's helpful and useful for this characterization of multiphoton distinguishability. Maybe in condensed matter, it may prove useful as well. I just don't know much about it.
Okay, thank you. Some more questions?
Hi, thank you for the nice talk. So this kind of unitary invariants usually appear in the numerator of linear and non-linear response functions. Have you considered analyzing that in the light of this formalism of unitary invariants?
No, but that could be an interesting thing. One place where I saw it appearing also in the numerator and the denominator was in weak values. So weak values appear in metrology, and actually you can show that the weak value is a ratio of third-order invariants and second-order invariants. So if you're interested in measuring a weak value in a direct way using a quantum circuit, that's one way of doing it. Maybe for linear response functions, that's also doable. Okay, if there are functions of these things, you can run circuits to estimate them. I won't show, it's already changed, but there are very simple circuits to measure these things. So you can prepare the states, do a control cycle permutation, control cycle gate, and you get estimates of these quantities. So anywhere where they appear, you can estimate them efficiently. So that could be helpful.
Yeah, this could be interesting because any nth order non-linear response function will be like your kind of unitary invariant of nth order and an energy denominator, basically.
So, for example, we noticed that auto-time order correlators, okay, are fifth order such invariants. So you can measure auto-time order correlator. We show how to do that in the paper.
Thank you.
Okay.
Okay, any short questions? Okay, I think if not the case, let's thank speaker.